So, we shall continue this completely immiscible liquid pairs. In the last video, we have started completely miscible liquid pairs and we completed completely miscible liquid pairs and partially miscible liquid pairs. So, let us continue this completely immiscible liquid pairs. So, completely immiscible liquid pairs means one liquid will not be soluble in the other. Two separate layers are formed when you take these two liquids. Suppose if you take two liquids A and B, these two liquids they are completely immiscible, they form two layers. So, in this completely immiscible liquid pairs, it is very useful in many industrial applications. Therefore, these two liquid pairs are immiscible. Examples of these type of liquid pairs: aniline water mixture, bromobenzene water, toluene water, many organic compounds, organic liquids with water, they form completely immiscible liquid pairs. In this completely immiscible liquid pairs, what happens here, in the liquid B, vapors, there is vapor pressure on the surface of liquid B. This vapor, the tendency of the liquid to go into vapor state is called vapor pressure. So, there is a vapor pressure of this B. But when this mixture is agitated, when this is disturbed, A and B, this mixture they form the vapors of both A and B. Therefore, this vapor pressure is the sum of the vapor pressures of both A and B. So, when the vapor pressure becomes equal to the atmospheric pressure, the liquid starts boiling. So, therefore, it can be distilled. So, therefore, these liquid mixtures A and B, for example, aniline and water, the pressure of aniline at 98 degrees centigrade is 7.07 kilopascals and that of water is 94.3 kilopascals. Total sum is 101.3 kilopascals, which is equal to atmospheric pressure. Therefore, when you take the mixture of aniline and water, the mixture starts boiling at 101.3 kilopascals. Similarly, bromobenzene and water, the total sum is 101 when that is in the mixture state. But individually, the boiling point of water is 101.3 kilopascals, whereas in the mixture, the boiling point is reduced because of the mixture of vapor pressure is equal to vapor pressure, atmospheric vapor pressure. Therefore, vapor pressure of the mixture PA plus PB is equal to total P naught. This is the total pressure, total vapor pressure of the mixture of immiscible liquid pairs. So, total sum is P naught. Therefore, when a solute is dissolved, not like that, problems. And for example, in this mixture, these two components can be separated by steam distillation. Steam distillation, these two can be separated. So, this steam distillation, in this steam distillation, we have to take a distillation flask and you pass steam into this mixture. This is the mixture. You pass this into condenser. This is the steam. So, by passing steam into this mixture, it is possible to separate these two. They can be separated and on cooling, two layers are separated and they can be completely separated from the mixture. Therefore, by steam distillation of these immiscible liquids, it is possible to separate the liquids at lower temperature than their boiling point. In many cases, the boiling point, for example, the boiling point of aniline is 185 degree. Boiling point of aniline is 185 degree, but it distills at 101 kilopascals, which is the boiling point, which is the atmospheric pressure, which is very low than this annealing. So, at lower temperature, many liquids can be distilled. The advantage of this is many organic liquids, they decompose at higher temperature. Because when they decompose at higher temperature, it is very difficult to separate them from the source. In many organic source, organic compounds having higher molecular weight, they can be separated by this steam distillation. When mixed with the two liquids, the boiling point of organic compound or higher molecular weight compound reduces, and by passing steam, it is possible to separate that organic compound at low temperature. Hence, on distillation, on passing through the condenser, you will get the distillate. This distillate separates into two layers, water layer and compound layer. So, on cooling, this can be separated just by separating funnel. Using a separating funnel, you can distill. Therefore, the advantage of this immiscible liquid pairs is to separate or to isolate an organic compound in the pure state without any decomposition. This organic compound can be separated by this steam distillation. So, the vapor pressure, total vapor pressure of this mixture is equal to atmospheric pressure. Therefore, the organic compound distills at lower temperature when compared to its boiling point. Many of the liquids, as I told you, they decompose at their boiling point. For example, nitrobenzene. If you separate nitrobenzene decomposes. Therefore, nitrobenzene boiling point is 210 degree. Boiling point of nitrobenzene is 210 degree centigrade. Therefore, at this temperature, what happens when you distill nitrobenzene only, it decomposes. This nitrobenzene decomposes at 210 degree centigrade. Therefore, it is purified, it is separated by this steam distillation. On passing this steam through the mixture, through nitrobenzene, at lower boiling point, nitrobenzene distills over and pure nitrobenzene can be collected and separated. That is the advantage of this completely immiscible liquid pairs. So, here we can calculate the weight fraction. Weight fraction, we can determine the molecular weight. Molecular weight using this weight fraction. For example, you know that partial vapor pressure of a component is equal to its mole fraction into its pressure in the pure state. This is Raoult's law. Raoult's law states that the partial vapor pressure in a mixture is equal to its mole fraction into its pressure in the pure state. If you take two components A and B, if two components A and B, this component A, this is component B, this is the vapor state of both the liquids on agitation. On agitation, both the liquids, they form vapors. This vapor pressure is nothing but the vapor pressure of both the liquids. Let us say it is P naught. Now, if you take the partial vapor pressure of the component A, Pa is equal to Xa into P naught according to Raoult's law. Similarly, partial pressure of B here is equal to its mole fraction in this liquid into P naught. Into P naught. Therefore, P naught by Pa by P naught, P naught cancelled over. So, Pa by Pb is equal to Xa by Xb. Xa is nothing but the mole fraction, its fraction in the vapor state, and Xb is the fraction in the vapor state. Xa is nothing but number of moles of A divided by total number of moles of A and B. Similarly, Xb is equal to number of moles of B divided by total numbers of A and B. Therefore, this cancels each other. Therefore, Pa by Pb, partial pressure of the component A divided by partial pressure of the component B is equal to Na by Nb, number of moles of A divided by number of moles of B. Number of moles of B is nothing but weight weight of A divided by its molecular weight divided by weight of B divided by its molecular weight. Okay. Partial pressure of A divided by partial pressure of B in the vapor state is equal to Na by Nb or W A by Ma. So, this can be rearranged as Pa by Pb is equal to Wa by Ma into Mb by Wb. So, this is the partial pressure of A, partial pressure of B, this is the weight fraction of A, this is the molecular weight of A, molecular weight of B divided by weight fraction of B. Now, you come to the weight fraction Wa by Wb, weight fraction of component A and component B in this vapor mixture is equal to Pa into Ma divided by Pb into Mb. So, this is the relationship to calculate the weight fraction in the vapor state Wa by Wb. That means the vapors you distillate, collect the distillate, in the distillate this is the fraction of A and this is the fraction of B. This ratio W by Wb is equal to Pa into Ma divided Pb into Mb. So, if we know the partial pressures of each component in this mixture and their molecular weight, you can calculate the weight ratio in the distillate. How much will be distilled? What is the percentage, weight percentage of the components in the distillate that we can calculate by using this formula. So, a problem is given here, a mixture of bromobenzene and water, this is at 92.5 degree, at which partial pressure of bromobenzene is this much and water is this much. The ratio of the distillate is 1:62:1, calculate the molecular weight. So, here let us say A is bromobenzene or and B is water. So, A is bromobenzene and B is water. Here the ratio is given. The ratio is given. Bromobenzene 1.62 divided by 1. Bromobenzene partial the ratio of the distillate, this is the ratio, is equal to weight fraction. Weight fraction is given, the ratio of the distillate is given. Partial vapor pressure of A, bromobenzene 15.86 kilopascal, and partial vapor pressure of water is given here, it is 85.46 into Ma by Mb. Ma is bromobenzene and molecular weight of water. Molecular weight of water is 18. So, this is the ratio 1.62 divided by 1, that is the ratio of the distillate given here, that I have substituted in this formula, and this is 15.86 is the partial pressure of bromobenzene 15.86 kilopascals and partial pressure of water is 85.46 into Ma, molecular weight of bromobenzene that is to be calculated, and molecular weight of water is given 18. Therefore, Ma means molecular weight of bromobenzene. Molecular weight of bromobenzene is equal to 1.62 into 85.46 into 18 divided by 15.86. Therefore, if you simplify this, you will find that molecular weight of bromobenzene is 157.38. Answer is given here, so you will get the answer. Therefore, by steam distillation of the mixture, it is possible to calculate the weight of the distillate obtained, weight percent of the distillate obtained, and also it is possible to calculate even the molecular weight. So, we have calculated here the molecular weight of bromobenzene 157.38 by this steam distillation. So, that is the application of steam distillation. By using this using this immiscible liquid pairs, it is possible to calculate the molecular mass of one of the components and also weight percentage here. That is the advantage. Now, what are the conditions for this immiscible liquid pairs to separate? So, one thing is that component should be insoluble, both the components should be insoluble. In such a case, you can use this, and also the molecular weight of the one of the component is very high. In case of organic solvents, organic compound, that can be calculated. Those are the advantages here. And in this case, another important thing is similarly we can calculate. Now, let us come to Nernst distribution law. So, this is about completely immiscible liquid pairs, examples of immiscible liquid pairs and distillation. The components, both of them, they reduce, the boiling point is reduced and they can be separated, and it is possible to calculate the weight fraction and molecule. That is the details that we have to study in detail about this completely immiscible liquid pairs. Now, come to the advantages of this immiscible liquid pairs, and what are the other advantages of this immiscible liquid pairs here. Now, come to next topic, that is Nernst distribution law. Now, we have these two completely immiscible liquid pairs. Now, we shall discuss what happens if a solute is added to these immiscible liquids. When a solute is added in this, what happens? That solute is soluble in both the solvents, but their solubility amount will be different in both the solvents. In such a case, what happens? For example, if you dissolve iodine in carbon tetrachloride and water, carbon tetrachloride and water are completely immiscible liquid pairs. Now, what happens when you add iodine to this carbon tetrachloride and water? When you add iodine, is soluble in both water and carbon tetrachloride, but the amount of solubility is different. The degree of solubility is different in water and carbon tetrachloride. In such a case, what is the advantage? What are the advantages of this type of solute soluble in different degrees in both the solvents? In such a case, a law has been proposed, that is Nernst distribution law. Then this Nernst distribution law says that when a solute is added to a pair of immiscible liquids, then the concentration of the solute soluble in these two immiscible liquid pairs, the ratio of these concentrations is a constant at constant temperature. That is Nernst distribution law. Nernst distribution law, once again I repeat it, when a solute is added to a pair of immiscible liquids, the amount of solute, the ratio of the concentration of the solute soluble in two immiscible liquids, that ratio is always a constant at a constant temperature. That is the law. So, mathematically we can write this is, suppose if A is one of the liquids immiscible, B is another liquid, we have added a solute, that solute is soluble slightly in both the solvents, then the concentration of that solute in first liquid divided by concentration of the solute in the second liquid is always a constant. This constant is called partition coefficient or distribution coefficient. Therefore, that is a law. Nernst law says that a partially soluble solute is dissolved in a pair of immiscible liquids, then the ratio of the concentration of the solute in two liquids, the ratio C1 by C2, this is first liquid, this is second liquid, concentration of the solute is C1 in the first liquid, C2 in the second liquid. This ratio is always constant at constant temperature. This constant is called partition coefficient or distribution coefficient. For example, if you take iodine and you take water and carbon tetrachloride, iodine is soluble in water and iodine is soluble in carbon tetrachloride, but their solubility is different. The degree of solubility is different. Therefore, this ratio is always 85. This ratio of iodine in carbon tetrachloride and iodine in water is 85. So, it is a constant at room at 25 degree centigrade or at 25 degree centigrade. The ratio of iodine soluble in water and carbon tetrachloride. So, this is water, this is carbon tetrachloride and this is water layer, this is water. So, this ratio carbon tetrachloride, iodine in carbon tetrachloride and iodine in water is always constant. For a carbon tetrachloride water system, the constant is 85. Like that, different solutes are soluble in these immiscible liquids and it is a constant at constant temperature. This is Nernst distribution law. The ratio of the solutes in two immiscible liquids, the ratio of the concentration of the solute in two immiscible liquids is a constant, and that constant is called distribution coefficient or partition coefficient. So, a problem is given here for that calculation. When varying amounts of iodine were shaken with carbon tetrachloride and water. So, the same system they have taken here, carbon tetrachloride and water, iodine is added and it is shaken. So, when the mixture is shaken, the concentration of iodine were obtained like this. That is, the amount of iodine in carbon tetrachloride is 5.1. That is 5.1 grams per 100 ml, 5.1, and water, the amount of iodine soluble 0.06 grams, and if you come to second concentration, iodine concentration is varied and it will be 10.2 and 0.11, and another concentration, some more of iodine is dissolved in the immiscible liquids and its concentration is 15.2 grams per 100 cc and this is 0.178 grams. Now, if you take the ratio 5.1 divided by 0.06 and 10.2 divided by 0.119, 15.2 divided by 0.178, in all these cases, in all the three cases, it is comes out to be around 85. So, if you take the average of these three values, that constant K, this constant K is found to be 85, on an average 85. So, this proves this Nernst distribution law. So, this constant K is equal to 85 irrespective of the amount of solutes used in different mixtures, like that. So, thus Nernst distribution law is verified. So, therefore, that K can be calculated, and also it is possible to calculate the proportion of the solute in two liquids. Suppose if you take water and nitrobenzene, two immiscible liquids, then what happens? At 101.3 kilopascals, nitrogen and water boils at 99 degree. The vapor pressure of water is this much, and find the proportion of water and nitrobenzene. Isn't it so? Now for that we have to use this expression, weight percentage. WA by WB is equal to PA into MA divided by PB into MB. We have derived that expression here. Using this expression, we can find out the percentage, weight percentage of water and nitrobenzene in the mixture. So here we have to calculate weight percentage of water and nitrobenzene by knowing the vapor pressure. P vapor pressure of water, P water is given, P water 97.72 into molecular weight of water 18, molecular weight of water 18 divided by weight percentage of water, vapor pressure of water 101.3, boils at 99, vapor pressure of water 101.3 minus 97.72. This comes out to be 12.5 100 minus 7 3.58 degree. Partial vapor pressure of water is nitrobenzene is 3.58 into, so we have to calculate what is that molecular weight of B, molecular weight of nitrobenzene we have to calculate. Find the proportion of water and this using. So you substitute the molecular weight of nitrobenzene here, molecular weight of nitrobenzene. So you can find out the percentage, find out the weight percentage. So if you know the weight of one of the component, you can find, or you can calculate the amount of the weight of water present in the distillate, weight of nitrobenzene present in the distillate. You separate these two and calculate the weight percentage. So weight percentage can be calculated, and this partition coefficient can be calculated. These are various methods to find. So now the conditions for this Nernst distribution law to obey is that the two liquids must be completely immiscible, and temperature should be constant, and the solute you have to use little amount of the solute, which is soluble in both the solvents A and B, little amount of the solute, constant temperature. And another important thing is that solute should be in the same state in both the phases, both the layers. In both the layer, first layer and second layer, in both the layers, that solute should be in the same state. That means it should not associate or it should not dissociate. There should not be any association or dissociation, and that solute should not be reacted with other components present in the mixture. So these are the conditions for the immiscible liquids to obey Nernst distribution law. Three conditions. First condition is the liquids must be completely immiscible. This is first condition. Second condition is less amount of the solute. Less amount of the solute should be used. And third condition is temperature should be constant. And fourth condition is that solute should be in the same state in both the layers. They should not undergo association or dissociation in any of the liquids. Same condition should be there. And condition number 5 is that solute should not react with any other component present in this layers. So these are the 5 conditions to obey Nernst distribution law. Now let us discuss what happens when there is association of the solute in one of the solvents and where is when dissociation is there in one of the solvents. So, as I told you, the different conditions of the validity of the law. So, liquids should be completely immiscible, low amount of the solute should be added, temperature should be constant, and the solute should not associate or dissociate in any one of the solvents. Another condition is the solute should not react with any of the components in either of these two. These are the conditions for the validity of the law. So, this very important limitation is association or dissociation. Association or dissociation. Association of the solute means, for example, succinic acid. If this is the solute dissolved in benzene and water, in benzene it undergoes dimerization. Succinic acid undergoes dimerization. Dimer is formed. Two molecules they join together to form dimer in benzene layer. So, this is association. And many of the solutes they undergo dissociation. For example, strong electrolytes, when you take two liquids, in many of the electrolytes they undergo dissociation in water, whereas they do not undergo any dissociation in organic layer. So, therefore, association or dissociation is one of the important limitations of this solute, immiscible liquid pairs. Now, come to what happens when there is association of the solute in one of the solvents. As I told you here, dimerization of succinic acid takes place in one of the solvents. Now, let us take a two liquid system. This is phase 1 and this is liquid 1 and this liquid 2. Now, you dissolve, you add the solute in this immiscible liquid. This solute undergoes that solute is soluble in solvent 1 and solvent 2. The concentration of the solute in the first phase is C1 and the concentration of the solute in the second phase is C2. According to the law, according to Nernst distribution law, the ratio of the concentration C1 by C2 is a constant. This constant, as I told you earlier, its partition coefficient or distribution coefficient C1 by C2 is a constant. But when there is association, association means, for example, n molecules of X in this phase 2, n molecules of X undergoes association to form Xn. This undergoes association to form Xn in one of the liquids. In another liquid it will be in the pure state. There is no association or dissociation in the first layer. Whereas in the second layer, what happens? This solute, for example, succinic acid undergoes dimerization. Like that, if in one of the liquids, if the solute undergoes association, we can represent that as Nx reversible error mark Xn. Now, you apply the law of mass action to this equilibrium. So, equilibrium constant K equilibrium is equal to concentration of the product Xn divided by concentration of the reactant, x to the power n. So, according to the law of mass action, the rate of reaction is directly proportional to the concentration of the product. In the reversible case, concentration of the reactant. Therefore, K equilibrium constant is equal to concentration of Xn product by concentration of the reactants. Now, you take this x to the power n, this side, and it becomes K equilibrium constant into concentration of Xn, concentration of Xn. Concentration of Xn, concentration x to the power n is this. So, therefore, concentration X is equal to nth root of this constant into Xn concentration. This Xn concentration is nothing but C2 Xn concentration, because here Nx undergoes association to form Xn. So, now concentration of C2 becomes Xn becomes C2. Therefore, this becomes nth root of concentration into C2, where K is a constant, nth root of C2. Therefore, concentration of C2 is nothing but nth root of C2. You substitute that here in this case. So, C1 by root of nth root of C2 is equal to K. So, this is the equilibrium constant when there is association. When n molecules undergo association, this value of n may be 2, 3. If the dimerization takes place, n is equal to 2, trimerization n is equal to 3, like that. So, C1 by nth root of C2 is equal to K. So, this is the equilibrium, Nernst equation for a system where there is association in one of the solvents, C1 by nth root of C2. For example, to verify this, to find out the value of n, an experiment is given here. Succinic acid has the molecular, succinic acid molecule in water, succinic acid has molecular weight in water. In the distribution of the acid between water and benzene, concentration of succinic acid in benzene 0.15, C2 2.42, 0.15, 0.289 by 9.7. Therefore, if you calculate this ratio, it will not be constant. The ratio will not be constant, and that ratio is found to be in this case it is 0.062, in this case it is 0.047, in this case it is 0.043. This ratio is not constant in case of succinic acid dissolved in water and in benzene system. So, this molecular determines, here we have to find out the molecular weight of the succinic acid. So, this is the ratio which will not obey the Nernst distribution law. So, therefore, if K is not constant, now if you substitute these values in this equation, K is equal to C1 by square root of C2. You substitute this. So, you take the square root of these values, then it is found to be constant, and it is found to be constant. K is equal to C1 by square root of C2 if you take, that is C1 by C2 is equal to 0.15 divided by square root of 2.42, comma 0.195 divided by square root of 4.12 and 0.289 divided by square root of 9. Now, if you take this ratio, it is found to be constant 0.096, and 0.093. Now, you see, if you take C1 by C2 ratio, its value is 0.062, 0.47, 0.03, no constancy, therefore it will not obey Nernst distribution law. Now you change the concentration into square root. If you take the square root, ratio becomes constant, 0.096, 0.096 and 0.0. This indicates that there is dimerization in one of the solvents. So in one of the solvents, so here n is equal to 2, n value is equal to 2, therefore there is dimerization. You can easily find out, oh, dimerization is there in the solute. From this dimerization value, we can determine the molecular weight. So like that. So that is the advantage of this. So by knowing the equilibrium constant, we can find out the number of molecules that undergoes association or dissociation, and using that we can determine the molecular weight of the solute when there is association of the solute. Now come to another case when there is dissociation of the solute. When there is dissociation of the solute, what happens when when there is dissociation, when there is dissociation of the solute in one of the solvents, what happens? Now we know if there is no association or dissociation, we will have the ratio C1 by C2, concentration of the solute in one liquid and concentration of the solute in another liquid C2. This is a constant. This shows that it is in the same state in both the liquids. But when there is association, this C2 becomes nth root of C2. What happens when there is dissociation? When there is dissociation, what happens? The dissociation, suppose you say if alpha is the degree of dissociation, alpha is the degree of dissociation, for example, ester undergoes partial dissociation in one of that. In such case, the concentration C2, this is second phase, this is first phase, and you have dissolved the solute in the solvent XX. In this case, what happens? This is C1 and this is C2. This undergoes dissociation. So C2 is not the exact concentration of the solute, because some amount of the solute undergoes dissociation. If alpha is the degree of dissociation, 1 minus alpha is the concentration of C2, because small amount of C2 undergoes dissociation, therefore remaining concentration is 1 minus alpha into C2. In such a case, the equilibrium constant K, partition coefficient or distribution coefficient K, can be written as concentration of the solute in the first layer divided by concentration. C2 becomes 1 minus alpha into C2, 1 minus alpha into C2, where alpha is the degree of dissociation. So by knowing the degree of dissociation, we can find out the concentration of C2 in one of the liquids, or by knowing the concentration C2 and C1, we can find out the degree of dissociation in one of the solvents. Therefore, you can use this expression for dissociation, and we can use this expression for, where is that, for association. So this is the expression for association, and this is for dissociation, and this is for no change. For no change, K is equal to C1 by C2. For dissociation, K is equal to C1 by 1 minus alpha into C2. For association, K is equal to C by nth root of C2. These are the expressions used here. Now, lastly, we have one of the important concepts, applications of this immiscible liquid pairs. In this immiscible liquid pairs, there are so many advantages. Large molecule compounds can be isolated without any dissociation. One of the important applications of this is extraction, solvent extraction technique. Solvent extraction. Here, one of the important applications of this. So we shall continue this solvent extraction in the next video.